In this video, we're going to be going over ions, isotopes, and relative atomic mass, and working out exactly what these numbers in the periodic table that you'll be given in your exam actually mean. There's a lot of information here, and a lot of it is hidden. So, with that said, let's do it to it. First up, let's look at ions. So for our purposes, an ion we're going to define as an atom or a molecule in which the number of protons does not equal the number of electrons. Okay, so remember, protons positive and electrons, symbol for an electron, is negative. Neutrons are neutral, they don't have any charge. And they have an equal but opposite charge, protons and electrons. So if there are more protons than electrons, it is a positive ion. And conversely, if there are more electrons than protons, it's a negative ion. So ions are only ions if there is a different number of protons and electrons. If the number of protons equals the number of electrons, it has no net charge, it has a neutral charge. It's not technically an ion, it's just an atom or a molecule. You may see ions being described as anions and cations. Which one is which? Well, anions are negative, cations are positive. How do you remember it? Cats are positive. Cats have paws, cats are positive. That's a really stupid mnemonic, but it's the one that I know. If you know any good ones, let me know. But that's the one that I remember. Cations are positive, anions are negative. Let's have a look at how this would work. So here we have a simulation on the PhET website. I'll leave a link in the description below. My advice is to just go on PhET and just play around with it. It's a really, really good learning experience. Just to play with things and see what happens. What I've got here, I've got the shell of an atom. So this is where the nucleus is going to go. We're going to pretend that an atom looks like this. Obviously, it doesn't look like this. This number down here is the atomic number. This number up here is the mass number. So notice they're going to mean different things. This number up here is going to be the charge. So let's have a proton. Let's put it into the place where the nucleus would be, and it becomes hydrogen. It's a positive ion. There is one more proton than there are electrons. There's no electrons. So 1 minus 0 is 1. So it has a charge of 1 plus. Notice the way it's written there. It's not plus 1, it's 1 plus. And it's to the top right hand corner of the H, the symbol there for hydrogen. If I have an electron, put it in the first energy shell, it's now a neutral atom. Nothing changes here, but this goes to 0 because protons equals the number of electrons. It's now no longer an ion, it's a neutral atom. Again, I take it away, it becomes positively charged. I put it in, it becomes neutrally charged. If I put in another electron, now there are more electrons than there are hydrogens, than there are hydrogen protons. It's now negatively charged. 1 minus 2 is negative 1. It's also going to stay stable. It would probably be fairly easy to ionize, I imagine. Okay. What happens if we put a neutron in? Let's take an electron out. What happens to the charge? Well, nothing happens to the charge. Neutrons are neutral. They don't affect the charge, but notice what's happened up here. It's still hydrogen because it has one proton. But now there are two things in the nucleus. There's a proton and a neutron. What I've just done here is I've made a different isotope, which we're going to get to next. But notice something here. This number down here, the atomic number, really is kind of a redundant number because all hydrogens have one proton. It's there because it makes things easier when we add atoms together, molecules together to make atoms together to make molecules, but it is kind of redundant. This would be hydrogen 2. So this would be deuterium. This would be, what's it? Protium, I think it's called, just off the top of my head. So this is protium hydrogen. This is an isotope of hydrogen. This is deuterium. This is tritium. This is unstable, so it's going to want to decay. We're going to get to isotopes in a second. Okay, if we have another proton, we put it in here, what are we going to get? It's going to become helium, magically become helium. Obviously, it's a lot harder in real life. If you could just miraculously change hydrogen into helium just by moving something on a screen, you've created cold fission and you'd be Nobel Prizes coming your way. But there is a positive one charge because there are two protons and one electron. We put a electron in there. Electrons are negatively charged. It's now a neutral atom. It's no longer an ion. If we put another proton in, it becomes lithium. But still, the number of protons matters. We put a neutron in there just to balance it out. We put an electron, it's not going to go in the inner shell. It only fits 2 electrons. It has to go in the outermost valence shell. So we would call this lithium 6. And the 3 there is redundant again because all lithium has 3 protons. So we will call this a lithium 6 neutral atom. If we had another electron, we would now call this a lithium 6 cation, -1 cation, or 1 minus cation. Sorry, an anion. I'm breaking my own rule. It would be an anion. So what about isotopes? What are isotopes? Isotopes are technically everything is an isotope. Every atom is an isotope. And when we use the word isotope, generally though we mean that the number of neutrons does not equal the number of protons. So let's have a look at some examples just to show you. So here's another PhET simulation. So here we have hydrogen 1, so protium. Why they call it myocyte, I don't know. We'll just ignore the electrons for now. There is 1 proton and it has a mass number of 1. It has an atomic mass of 1.00783. Why is there a difference there? Well, there's difference there because you're going to need quantum physics and modern physics to do that, which is year 13. But there is a nuclear binding energy in here which changes the mass somewhat. If you remember Einstein's famous equation, E = mc squared, energy and mass have an equivalence related to the square of the speed of light. That's c squared. So we're going to sort of presume that it's 1.007. Okay, there are no neutrons, so this is hydrogen 1. If we put a neutron into the nucleus, it's now deuterium. The mass almost doubles. Doesn't exactly double, again, because they need energy to bind. There are two numbers here in the nucleus with the mass, in an atomic mass unit. Remember, an atomic mass unit is 1/12 of a carbon-12 atom. But notice something interesting here. This isotope, its abundance in nature is 0.0115%. So of all the hydrogen on Earth, 0.0115% of it is hydrogen 2. If we take out the hydrogen, the neutron, we see that 99.9885% of it is hydrogen 1. You might be asking yourself, well, what about hydrogen 3? And this is a little bit harder to nail down its trace. And it's around about 1 in a couple of billion. So it's very, very, very rare would you have hydrogen unless you specifically, hydrogen 3, unless you specifically really, really wanted to use it. And you won't be doing that in high school. But it is possible to have hydrogen 3, and it has an atomic mass unit of almost exactly 3. Okay. So there are 3 main isotopes of hydrogen. Hydrogen 1, which has 1 proton, no neutrons. Hydrogen 2 is the next isotope, and that has 1 proton and 1 neutron. Again, it always has to have 1 proton, otherwise it's not hydrogen. And then there is hydrogen 3, which is unstable. It's going to decay, which we'll get to at a later date. We could theoretically have hydrogen 4, but you would have to go out of your way to make that. Okay, let's have a look at carbon, because we are going to work out relative mass. So this is carbon-12. There are 6 protons. All carbon has 6 protons. That's what makes it carbon. It has 6 neutrons. So this is carbon-12. Notice the atomic mass of this, by definition, is 12. This is what the atomic mass unit is based on. So 1/12 of this would be 1 atomic mass unit, which is slightly less than 1 proton and 1 neutron and a hydrogen atom. But for now, we're not going to worry about those binding energies. Notice here the difference in the relative abundance. 98.93% of carbon on Earth is carbon-12. It's great. It's very, very, very stable. It's cheap to make. It's abundant, and it's easy to isolate. Let's add a neutron. We now have carbon-13. This is less common. It's also stable, so it's not going to decay on us, but it's only 1.07% of all of the carbon on Earth. And this has a mass of 13.00335. And if we add another neutron, it's now unstable. There are too many neutrons for the protons to keep the nucleus together. This is carbon-14, and it has a mass of just slightly more than 14. And there are trace amounts of this. So negligible amounts of carbon-14. Carbon-14 is really, really important in carbon dating because it decays at a very, very predictable rate. I think it's 5,700 years. And if we measure the ratio of carbon-14 to carbon-12, we can work out how old something is. It's the basis of carbon dating. Okay, let's have a look at the numbers of carbon-12 and carbon-13. Again, we could have carbon-11, but it doesn't really appear in nature, I don't think. I don't think carbon exists on its own. We're going to work out the relative atomic mass of carbon. So notice here that the atomic mass is 12 and the abundance is 98.93. So let's just note those numbers. Carbon 12, mass of exactly 12, 98.93%. Carbon 13 has a mass of 13.00335 and has an abundance of 1.07%. Carbon 14 is negligible amounts. So I'm just going to note those, and from this we can work out the relative atomic mass. So this is relative atomic mass is a topic that really throws a lot of students. It's really the weighted average mass of an element on Earth. Okay, and we work it out, so the mass of that is going to be the sum of the mass of an isotope, that's the rubbish bin in the background, times the relative abundance. In other words, how much of it is there in nature. And we now have enough to work out the relative atomic mass of carbon. Remember, we had carbon 12 and carbon 13. So carbon 12, the mass of that was exactly 12. What was the abundance? It was 98.93%. We need to turn that into a decimal fraction, so we're just going to move the decimal place 2 places to the left. So that's going to be 12.0 times 0.9893. Then we had carbon 13, and that had a mass of just over 13, so 13 point, let's just check, 00335, and that had a relative abundance of 1.07%, so 0.0107. Okay, and if we add those together, we're going to get the weighted average of carbon on Earth. So we go to Mr. Casio, 12 times 0.9893, 11.8716 atomic mass units, and for carbon 13, the mass of that is 13.00335 times 0.0107 is that, so 0.1391 atomic mass units. Okay, and then we add them together. That's what the sigma bit here means. We add them together. So the relative atomic mass of carbon is going to be 11.8716 plus 0.1391, and Mr. Casio is going to help us out. Let's clear that. So 11.8716 plus 0.1391, 12.0151. So what does that mean? That means if we had a mole of carbon, we would expect it to be 12.0151 atomic mass units on average. Some of it is going to be carbon 12, some of it's going to be carbon 13. A tiny amount will be carbon 14, I guess, but very rarely. And why is this important? If we go to the periodic table and we have a look at carbon, we see that the relative atomic mass of carbon is 12.0, and it only goes to one decimal place. So let's do the same for boron. Boron, it's a little bit more interesting. It's not quite 11. Let's have a look. So it's going to have 5 protons, and it looks like most of the time it's going to have 6 neutrons. But let's test it out. Let's go to PhET. Let's go to boron. So boron 11 is the most abundant isotope of boron. So obviously it's got 5 protons, 11 things in its nucleus. So therefore it must have 6 neutrons, and it has a relative abundance of 80.1%, and the atomic mass is that. What are the other isotopes of boron? There is boron 10, and that's 19.9% of boron. Boron 12, none of that. Is there boron 9? No. So the only isotopes that are going to matter are going to be boron 10 and boron 11. So let's take the numbers. Boron 10 has a mass of 10.01294 and a relative abundance of 19.9%. And the more common boron 11 has a mass of 11 and change and has an abundance of 80.1%. Let's do the maths. Okay, boron. So the atomic mass of boron is going to be, let's have a look, just reading my notes. So boron 11 had an atomic mass of 11.00931, and its relative abundance as a proper fraction, or as a proper decimal fraction, was 0.801. Plus, now boron 10 had a mass of 10.01294 and a relative abundance of 19.9%, which is 0.199. So we add those together, we get Mr. Casio to do the hard work for us. Brackets 11.00931 times 0.801 plus 10.01294 times 0.199, and we get 10.811. So that is the relative atomic mass. So 10.811. And if we go to our periodic tables, 10.8. Well, it's rounded there to 1 decimal place. Okay, that's how we do this. So just to recap, an ion is when the number of protons does not equal the number of electrons, giving it a charge. An isotope is any element, but really we mean the number of protons. We just have the noisiest trash collectors. Does not equal the number of neutrons. And the relative atomic mass is the weighted average of the atomic mass of an element, and the atomic relative atomic mass is the sum, so everything added up, of the atomic mass, times its abundance. Okay, one last thing, an anion is negative, so there are more electrons than protons, and a cation is positive because cats are positive. So there are more protons than electrons. So it's going to have an electric charge, a net electric charge. And that's that.